Here I'm going to introduce our recently published work. The title is Point Cloud Instance Segmentation using Probabilistic Embeddings. It is a joint work with Professor Peter Wonka. In image classification, we want to find a label for this whole image. In object detection, the goal is to find bounding boxes for all objects. In semantic segmentation, the output is pixel-wise semantic labels. Additionally, instance segmentation needs to obtain pixel-wise instance labels too, which means we need to differentiate between different instances, like the shape in this image. A point cloud is usually obtained by 3D laser scanning. It has a lot of applications, like preserving the structures of buildings, scenes, streets, and objects. In this work, we did the experiments on the dataset PodNet, which contains a lot of daily objects like bags, chairs, and tables. We take a raw point cloud as input, then output point-wise semantic and instance labels at the same time. In the literature of instance segmentation, the key is to measure similarities between points. Usually, people choose Euclidean or cosine distances, which have drawbacks, like high-dimensional embeddings. On the contrary, we propose to use probabilistic distances. We assign a distribution to each point, thus each point is actually a random variable. Actually, there are many ways to measure distances of random variables, like the famous KL divergency. In this work, we choose this equation for two reasons. First, it is symmetric. Second, it is normalized. The value is between 0 and 1. We show the qualitative results in this video. In the left, ground truth; in the middle, PodNet; in the right, our results. It's obvious that our method is able to detect more instances than PodNet. Here we visualize the embedding space. We show the deterministic embeddings in the left and the proposed probabilistic embeddings in the right. We can see that the probabilistic embeddings outputs smaller deformations to the original point clouds, which means they are easier to train comparing to deterministic embeddings. This also explains why our method is better. This table shows the quantitative results. Our results are better for almost all categories. Thank you all for your attention.